It's a pleasure to have you everyone here and to share my thesis project on automatic symbolic goal abstraction via reachability analysis in hierarchical reinforcement learning. So the motivation behind this research is the fact that the advances made in artificial intelligence has allowed robots to be much more autonomous in accomplishing their tasks. So in levers like capabilities in perception, robots are much more capable of understanding large quantities of data around the world. And this in turn gives them higher and more autonomous abilities to make decision making. And then last but not least, robots are capable of sophisticated means of communication by understanding human language, human gestures, and even facial expression. And they're even capable of generating their own dialogue. The focus of today's presentation and my thesis is around decision making. So why is autonomous decision making in robots such a hard problem? So first, planning is difficult to engineer. Humans often have to design solutions that are fit perfect for a specific problem, and they have to describe it very well and account for all the possibilities to solve a task. Additionally, it is difficult to implement any change in these solutions once you have some change in your environment. The second main difficulty is around transfer. So when human engineers develop some planning solution for a particular task, it is often difficult to implement it or to adapt it to another task, which might even be very similar. And then third is the struggle or the lack of interpretability, because the advances in AI and neural networks have created this problem where decisions that are made by robots are often opaque to humans and cannot be interpreted. A very popular approach for autonomous decision making is reinforcement learning. And so reinforcement learning often involves an agent that is repeatedly interacting with its word to learn some policy or some action policy to accomplish a task. So specifically, this agent observes some state which conveys the information about its word, and it also receives a reward signal, which is a real value, denoting how successful it has been at accomplishing this task. And then this agent updates its policy to maximize a cumulative reward signal, basically translating the success in this task. This policy is actually a function that is capable of selecting actions into the environments that are either oriented towards exploring more information into this environment and uncovering where the rewards are hidden, or favoring more maximizing these reward signals to capitalize on the knowledge that the agent has already acquired. And then finally, once an action has taken place into the environment, this environment transitions to a new state. A particularly difficult breed of tasks for reinforcement learning is the long horizon tasks. And so these tasks often require achieving intermediate milestones before the task is finished. Simple example is when a chef is making pasta. So this chef has to prepare a sauce, has to boil the water, has to put the pasta into the water before combining everything and serving. And so in between of every milestone that I showcase here, there are these smaller actions that have to be accomplished before the milestone is achieved. So let's look at an even simpler example of a maze where a robot has to navigate from a starting position to an exit position. Here, it is difficult to design a reward function that correctly and adequately conveys the behavior needed by the robot. And the simplest choice that engineers often default to is using some kind of distance metric or negative distance metric that denotes how far the agent is from the exit position. But this, while this function is intuitive, it doesn't actually guarantee good behavior. So in this case, if the robot goes to the right, it will get closer to the exit, but this is not the correct behavior and the robot needs to go up. And so with knowing the fact that these rewards can lead to local extrema, this can block the learning of the agent. So in this thesis, I study hierarchical reinforcement learning, which solves long horizon problems by decomposing them into smaller tasks. How does it do that? Well, basically by having two agents instead of one, where these two agents are organized in a hierarchical manner, such that a high-level agent picks goals for the low-level agent to achieve. Let's make this more concrete by looking at an example. So in this maze, our high-level agent will pick a goal, which is some position in this maze, and throughout, let's say, k number of steps, this low-level agent will try to approach it as best as possible. And this notion of reasoning over a temporally extended action is what I refer to by temporal abstraction in this process. And so this repeats on and on during the interaction until the task is hopefully accomplished. But I've shown you here that a goal can be a position in the maze, but this isn't the only choice. And the example that I will show here will expose some difficulties in the goal in designing the goal space. And so in this case, the agent, the high-level agent, might be tempted into picking G2 as the next goal because it's closer to the exit. But if the low-level agent moves to the position of G2, it will be backed into a corner. Bad behavior again. This is the same spirit of the example that we've seen before. It would have been better to move to this new G2, which allows the agent to reach the exit much more easily in the future. So here the observation that we can make, and that is essential in this research, is that goal spaces should capture environment dynamics. The second observation that I want to share is that human reasoning is actually symbolic. We reason over signs and symbols. We reason over human language. Our mathematics are full of symbols that have a lot of meaning. And so these symbols are often compact ways of representing information. They have semantic meaning behind them, and they are very general in the sense that they can be applied across different contexts. So one way that a human would intuitively think about this navigation problem is that we don't target particular coordinates in a space to move. We just think of it as rooms. Like I'm in this room G0, let's call it, and I need to move to the next room G1. And this view no longer considers that point of contention to be near the exit. It's actually in a very different room. And so the message here is that spatial abstraction needs to capture environment dynamic. So here I get to the main problem of this thesis, which is how can we automatically learn a symbolic goal space that captures environment dynamics and can be leveraged for an efficient hierarchical reinforcement learning. So the main challenges that I treat in this work is first, how to formulate an abstract goal space that captures environment dynamics. And then second, how can I remember that we want to build robots that are autonomous, and so we need to design an end-to-end algorithm that is capable of learning this goal abstraction from agent exploration data. Third, how can we ensure that it addresses high dimensional environments? And then fourth, how can we implement a mechanism in this algorithm to allow for human in the loop learning? And so contributions can be summarized as such. So first, I will present a spatial abstraction I call reachability-aware goal abstraction. And then second, I will present the Gara algorithm, which has been published in ICDL 2023. And then third, I will present the STAR algorithm, which extends the spirit of the Gara algorithm and allows it to scale to more difficult environments. And this work has been published in iClear of 2024. And then finally, I did during my thesis an exploration for implementing LLMs as a goal selection mechanism in STAR, but I will not present this today, and I will focus only on the first three contributions mainly. So let's start with the reachability-aware goal abstraction. So how can we create a symbolic abstraction that captures environment dynamics? An important notion that we can gather from the previous example is the fact that there is a discrepancy in the hierarchical reinforcement learning formulation here, where the high-level agent is unaware of what the low-level agent can reach. And so here, capturing reachability relations is essential to conveying the right information needed to solve the task. The high-level agent needs to know that the position of G2 does not ultimately reach the exit easily. I will try to introduce some fundamental aspects in this work before formulating the whole abstraction. And so I would like to first introduce the notion of set-based abstraction. A set-based abstraction is basically a function that maps a state into a set of states. It's kind of like S is mapped to a whole box, which represents a set. And this form of abstraction allows us to build a goal space that is composed of sets of states. Second, I would like to define what I refer to by reachability property. So an abstraction respects this reachability property between two abstract goals, Gi and Gj, if all of the states in Gi can move to some state in Gj through at most k numbers of steps by applying the policy that targets this goal. I would like to also highlight that I will refer with R of Ji Gj as the set of states that are reached starting from Gi. So here we are fully equipped to, I also want to stress that during this presentation, I will refer to concrete goals as goals that are formulated as states, and they are noted with lowercase g, whereas abstract goals are goals that are formulated as a set of states and noted through uppercase G. And now we are equipped to understand what this reachability abstraction looks like. And so let's assume that we have access to a theoretical optimal trajectory over concrete goals in the maze. The abstraction, the intuition behind the abstraction is that it is composed of sets of states that will sequentially lead us to the exit. And so the reachability-aware abstraction should verify the following properties. So first, every state needs to be contained in its abstraction, kind of like G1 is contained into the abstraction of G1. Second, the abstract goals should be disjoint. Third, and most importantly, the abstract goals in this optimal trajectory should verify the reachability property, meaning that every state in the abstraction of G1 should be capable of reaching some state in the abstraction of G2, and so on and so forth. And finally, a technical property where we need the abstraction of the final goal to have a bounded size. Now, we want to study if this abstraction actually impacts the way we learn policies for the agent. So By definition, abstraction refers to discarding some information and keeping some other information that we think is critical. But how can we ensure that this reachability-aware abstraction does not lose any critical information that we absolutely need to solve the task? So our way of assessing this area is by comparing the policies trained under the abstraction with an optimal policy that is trained in a concrete setting, meaning that it has access to perfect information. And so we will compare trajectories achieved by each policies to understand that. So I go back to my example where I show an optimal theoretical trajectory. And the intuition here is that a possible trajectory that navigates through the abstract goals will have a limited or bounded deviation from this optimal policy. This is because we have ensured the reachability property that says, even though these trajectories can diverge through the task, they will always have to converge or get closer somewhere because they will reach the same targets eventually. And so the theorem says that we have a bounded deviation for these trajectories. And then we would like to see if we can actually compute this abstraction. And so here, if we start from an abstraction that violates the reachability property in a specific couple of goals, GI and GJ, and assuming that we have access to all of the reachability relations, how can we compute the abstraction? So here in the schema, the reach set of states is outside, it intersects with GJ, but it's not completely a subset of it. So the process of refining GI actually splits it into two sets where we obtain GI prime and GI second, where GI prime reaches the target and GI second reaches some other partition or some other set that we don't care about. And here, this is how we've computed a new form of abstraction that verifies the reachability property in a couple of goals. Our theorem is that through a finite number of refinements, a reachability-aware abstraction can be computed. Now let's see how we can implement all of this process into a hierarchical reinforcement learning called Gara. And so I will start by showcasing how we can learn this reachability-aware abstraction online from exploration data. The process is multi-step and it adheres to this schema here. But first, I would like to explain the part where we use the exploration data of the agent to train a predictive forward model. So I define a K forward model, which is a neural network, FK, that takes a state, a target, which is an abstract goal, and it predicts the state that is reached by the agent after K steps. So if we assume that ST is the start, ST plus K is the real state that is reached, F of STG is some approximation of the state in blue. F here is trained directly from exploration data, and it borrows from the ideas explored in model-based reinforcement learning. Second, now we want to answer the question, which is, once we have a starting set, a target set, and a predictive model, how can we evaluate the reachability relation between these two sets? And so this schema here shows exactly the question that I asked. And a tool that we found is particularly helpful in answering this question is neural network reachability analysis. So neural network reachability analysis borrows from concepts studied in formal methods, and it basically allows us for a neural network and an input set. If we imagine that R is the image of this neural network over all of the input, neural network reachability analysis can allow us to have some over approximation R tilde of the actual ground truth R. So we apply that directly to the problem that that I just listed by basically computing or over approximating the set of states that is reached from GI to GJ. And this is how I can use neural network reachability analysis to assess the reachability relations between two sets. Finally, the reachability analysis process isn't 100% accurate, and we might need to split a starting set GI into smaller sets to allow for to have smaller sets where we reconduct the reachability analysis, where it would have more precision. And ultimately, if the reachability relation is decided, meaning that we detect that it's either satisfied or violated, then that's the output of this approach. Now, how do I integrate all of this into hierarchical reinforcement learning? Well, this is where the Gara algorithm comes in, goal abstraction via reachability analysis. Gara adheres to the structure of standard hierarchical reinforcement learning that I showed earlier, but it has this additional component of goal abstraction refinement, where it takes exploration data from the agent and it refines it by creating a new goal space that the agents can reason over. And the high-level agent here will select abstract goals that the low-level agent needs to reach. The example of the maze again. So let's imagine that I start with an initial course goal space composed of two sets G0 and G1. And the high-level agent picks G1 as the target. So through case steps, the low-level agent will try to navigate until it reaches G1. And so after doing this for a number of times, we can hypothesize that we have gathered enough training data to be capable of refining our goals. And this is how we can split the original G0 into two sets, G0 prime and G0 second, where intuitively all of the states in G0 prime can easily reach G1. And by easily, I mean in under case steps. And all of the states in G0 second cannot easily reach G1. A snapshot of some of the results that that I was able to get on a point maze environment that is low dimensional for Gara. And here I would like to highlight that so in blue is a hierarchical reinforcement learning agent that uses handcrafted goals. And this represents an intuitive baseline for goal spaces that outperforms all other HRL approaches. And you can see that the learned spatial abstraction by Gara reaches a performance that is comparable to these handcrafted goals. Second, it outperforms the other approaches also that it either use no abstraction or are just standard reinforcement learning without any hierarchy. And so here, the conclusion is that the reachability-aware spatial abstraction allows for efficient hierarchical reinforcement learning. And then the third part is, how do we address high-dimensional environments? So it actually turns out that there's a scalability problem with Gara. Crucial assumption that that is made in Gara is that once you have set a target G1, let's say, you can reach it and you can get exploration data that showcases what are the states that reach it. But in reality, in high dimensional environments, this may be not the case. So imagine if the agent just reaches this cloud of points and is stuck and cannot continue just because the goal is hard to reach. In this case, the agent is no longer able to refine its initial starting goal G0. So the solution to address the scalability of the abstraction is actually to introduce intermediate subgoals within the task that lead to G1 little by little and that are easier to reach. And so this process is formulated through a mid-level agent in the hierarchy that operates purely on a temporal abstraction basis. And so here I introduce the second algorithm of this thesis, which has been published in NICLEAR 2024, which is star spatial and temporal abstraction via reachability. And so this algorithm is composed of 3 levels in the hierarchy. First is the commander, which selects abstract goals. Second is the tutor, which is going to select these intermediate subgoals that are going to be little by little helpful for a controller that is going to take actions into the environment to best reach these intermediate goals. And of course, we keep the goal abstraction refinement process. So an example of how this works in practice is, again, the maze, where the commander here can select G1 as the abstract goal to target. And then the tutor is going to pick sub-goals into the environment that are easier for the agent to reach. And the controller will take the actions to approach it. Again, this process continues on for some time before we gather training data or exploration data for assessing reachability relations for the goal for the abstraction refinement. So once our goals have been refined, we can revert to the same result as earlier, where G0 prime is identified as the set of states that reach the target. Now, I will introduce some experimental evaluation of the star algorithm. And so here I list 4 main research questions. First is, do these spatial and temporal abstractions result in a more efficient learning? And then second, does the reachability-aware abstraction capture more complex environment dynamics? And remember that the first motivation of this work is to build an abstraction that captures these dynamics. Then third, how does the learned abstraction decompose the environment? And this is actually a question of interpretability. Fourth is, how does this abstraction learned by star transfer across new environments? And so I experimented with star on a set of continuous control environments where an ant robot composed of 8 joints and 4 legs has to navigate to some position within a maze. This environment is difficult because it has 30 dimensions for the state space, continuous, and 8 dimensions for a continuous action space. So for the ant maze, the first environment, I wanted to show something cool. For the ant maze, the ant has to go from the bottom part of the maze to the upper part. And for the second environment, ant fall, the ant has to navigate an environment where it needs to push a red movable block into a pit and use it as a bridge to cross to the second platform. And then third, the ant has to move near a camera, highlighted in red, and has to turn and face it before a gate is opened to allow it to cross to the upper side. So here we design a concrete goal space in each of these environments. So for the first environment, we choose X and Y as the variables for the goals that are essential to describe the task. And then for ant fall, we add the Z variable, just because we need to monitor the height of the ant and determine if it has fallen into the pit or not. And then third, we add the angles of the torso of this ant to actually determine if it's facing this camera or not. And through this increase of the dimensions of the goal space, we look at this as an increase in complexity of the dynamics of the environment. I compare with some various baselines from the research. And so in this study, we will see how STAR and Gara perform, where STAR is capable of both spatial and temporal abstractions, and it captures reachability relations. Gara is just capable of spatial abstraction, but it captures reachability. Third is Hero, which is a pillar work in the field of HRL, but it has no spatial abstraction and it has no mechanism to capture reachability or any environment dynamics. Fourth is Lesson, which is a more advanced version of Hero. And finally, we compare with HRAC, which is the work that is closest to STAR in the sense that it does not have spatial abstractions, but it leverages a mechanism to capture reachability relations between individual states, whereas in STAR, we capture relations between sets of states. And so here, I show the average success rate of all of these approaches in different environments. And so starting with ant maze, we can see that the spatial plus temporal abstraction is much more data efficient than just the spatial abstraction, just because Gara isn't capable of achieving any form of success. Also, STAR outperforms the algorithms that use just temporal abstraction, like Hero or HRAC. And this trend continues for the rest of the environments as well. And this allows us to answer the first research question, showing that combining these forms of abstraction leads to more efficient learning. For the second research question, we can see that through the gradual increase in dynamics complexity for these environments, STAR is capable of leveraging the combination of spatial and temporal abstraction to capture reachability relations that are much more complex versus HRAC, which attempts to capture reachability between individual states, but the dynamics get too complex for it in either antfall or ant-maze cam. And then here, I would like to stress the point that the abstraction should be interpretable and understood by humans. And so I did an exploration into uncovering what the decomposition of the task ultimately looks like by the end of the training process. And so here in ant-maze, from the left, you can see the decomposition of the task during some point in the evaluation. And to the right is later phases of the training. And the color grading corresponds to the frequency of visitation of each of these abstract goals in the maze. So we can see that the abstraction gets refined over time, where it starts by having these big blocks that are unaware of the dynamics of the environment and the obstacles. And then finally, it looks much more refined and it adheres better to the obstacles. And ultimately, the agent most frequently visits the region that contains the exit point. We again observe interpretable results in AntFall in the sense that the agent in the early phases of the training, I just want to highlight that the red box there is the movable block that the ant should use as a bridge to cross to the second platform. But we see that the agent identifies unrefined sets of states, but through time, eventually, it is capable of finding a bridge-like structure that it needs to cross to not fall into the pit. Finally, the question of transfer learning. So in this experiment, I train the star algorithm and the HRAC algorithm in a particular environment, and then I transfer the abstraction of star and what is referred to as adjacency network in HRAC, which is this mechanism that is capable of capturing reachability relations between individual states. And so we do two flavors of abstraction here, where the first is a transfer to a different environment configuration, kind of like going from an ant maze with 2 rooms to an ant maze with 4 rooms. The second flavor is much more challenging, and I like it better, which is transferring to an environment with different low-level dynamics. So going from a robot in the shape of an ant to a robot, from a robot with the shape of a point to a robot with the shape of an ant. So how does star perform? And so in the first transfer experiment, we can see that both HRAC and star are capable of benefiting from the transfer learning in the sense that they learn faster. This is explained by the fact that actually the trajectories between these two environments are not that different. The abstractions or the relations learned in one environment are immediately useful in the second environment. In the second transfer experiment, where we move from a point to an ant, we can see that HRAC doesn't perform quite as well when it's transferred, it doesn't improve quite as well when in its transferred version, and it's neither quicker nor reaches higher success rates, whereas star is capable of achieving faster learning. Here, the trick is that HRAC the relations that are learned specifically for the point robot by HRAC do not immediately transfer to the ant environment, because the point has so many different dynamics to the ant, whereas star, which is capable of spatial abstraction, zooms out this vision and captures much more intuitive reachability relations across sets of states. So to conclude, in this presentation, the reachability-aware goal abstraction has shed light on the fact that capturing reachability relations in hierarchical reinforcement learning offers a bounded suboptimality and can be computed. Gara has shown that spatial abstractions can indeed be learned in an end-to-end manner and concurrently with a policy in deterministic settings. Star shows that spatial and temporal abstractions in hierarchical reinforcement learning lead to more data-efficient HRL and captures abstractions that more resemble human intuition and can be applied or transferred across different tasks. And then fourth is the exploration that that I wasn't able to fit in the timeline of this presentation, which is the exploration of LLMs for goal selection. This has shown, or the early exploration and the early phases of experimentation have shown that the interpretability of the abstractions show promise in incorporating human in the loop process. So the takeaway message from this thesis to me is that spatial and temporal abstractions can be combined together to allow agents that decompose long horizon tasks in two ways. The first is adapting to the dynamics of the environments, and then second, to the capabilities of the agent itself and the policy. The second message is that this abstraction discretizes the state space, constituting an emergent symbolic representation for the algorithm. And this is the way to treat continuous and high-dimensional state spaces. And then finally, this abstraction shows some signs of interpretability, and the hypothesis is that this the semantic behind this abstraction is somehow linked to human representation of space. For future research directions in this work, I would like to think about the problem of capturing reachability relations in stochastic environments. Our everyday lives are characterized by high levels of stochasticity, from pedestrians moving on and about, from operating in warehouses where obstacles are added and removed continuously. And then the second question is, how can we learn abstractions in environments with partial observability? So this example of a robot that wants to open a door, but it doesn't know that it needs a key. Robots indeed have access to more sophisticated technology and sensors nowadays, but you do not necessarily can create a sensor to detect if you have a key or not. This is something that the abstraction mechanism should be capable of inherently capturing during the learning process. And then finally is the question of how can we introduce a human-in-the-loop process for the STAR algorithm, basically to allow for more usefulness out of this interpretability aspect of the abstraction that the algorithm gathers, and to create robots or machines that can better interact with humans, can receive instructions, can explain their behavior. I thank you for your attention, and this has been my PhD presentation.